The universe is not expanding forever. It may already be dying. Everything physicists built their models on may be wrong. The numbers don't add up. The crisis is real. The gravity matrix. Today, we investigate what is genuinely happening to the universe right now. Not the poetic version, the version the data is actually telling us. And the data, for the first time in decades, is genuinely frightening scientists. Cornell physicist Henry Tai recently stated something extraordinary and unsettling. He said the universe is like a rubber band stretched to its absolute limit. It can only stretch so far before it snaps violently back. New DESI data suggests the cosmological constant may actually be negative. A negative cosmological constant means expansion eventually stops and reverses. The universe could reach maximum size in just 11 billion more years. Then everything that exists would begin falling back toward a single point. A big crunch, the universe's total annihilation, arriving in roughly 20 billion years. But here is what makes this genuinely revolutionary. We may be witnessing it begin. For decades, the standard model of cosmology seemed unshakable and complete. Lambda CDM, 68% dark energy, 27% dark matter, 5% everything else. 5%. Every star, planet, galaxy, and atom you have ever encountered. The remaining 95% is invisible, undetected, and barely understood. That model held for 30 years. Then the cracks began appearing. The first crack arrived with a deceptively simple question about one number. How fast is the universe actually expanding right now? Edwin Hubble first measured this rate in 1929, establishing the expanding universe. His original estimate was wildly wrong, but the principle was revolutionary. Today, two precise measurements of that same rate fundamentally disagree with each other. Planck satellite data gives 68 kilometers per second per megaparsec. Supernova distance measurements consistently return 73, a 5 sigma discrepancy. 5 sigma means the odds of this being a statistical fluke are 1 in 3 million. This is not measurement error. Something fundamental about our model is broken. And just as physicists began accepting the tension, a third measurement arrived, 64. Researchers studying the Centaurus A and Mate 1 galaxy groups derived that lower value. 3 independent methods, 3 different answers, all conducted by world-class physicists. The universe cannot be expanding at 3 different speeds simultaneously. Either our measuring tools are flawed, or spacetime itself behaves differently than expected. One radical possibility: Our cosmic neighborhood expands slightly slower than the wider universe. A local gravitational underdense region could bias every nearby measurement we have ever made. But even accounting for this, the core tension between 68 and 73 persists. This persistent discrepancy has a name that physicists say with increasing unease: the Hubble tension, and it has refused to disappear for over a decade. Every new instrument, every refined technique has only sharpened the contradiction. Now enter the Dark Energy Spectroscopic Instrument, DESI, in the Arizona desert. DESI maps the universe using baryon acoustic oscillations, ancient pressure waves from the Big Bang. These acoustic rings act as a cosmic ruler, a fixed scale across billions of light years. DESI's first full data release in 2024 mapped 6 million galaxies across 11 billion years. What DESI found in that data sent a tremor through the entire cosmology community. Dark energy appears to be evolving. It is not the constant Einstein imagined. Einstein introduced the cosmological constant in 1917, then called it his greatest blunder. He added it to keep his equation stable, then removed it when Hubble proved expansion. In 1998, astronomers discovered the expansion was accelerating. The constant was resurrected. Saul Perlmutter, Brian Schmidt, and Adam Rees won the Nobel Prize for that discovery. The prize was awarded in 2011. The assumption of a constant dark energy seemed settled. DESI's 2024 data shattered that assumption with quiet, devastating precision. The dark energy equation of state parameter W appears to deviate from -1. -1 means constant. Any deviation means dark energy is dynamical, it evolves. UCL physicist Ofer Lahav noted, if dark energy evolves, the universe's fate becomes uncertain. Meanwhile, the Dark Energy Survey released its 6-year combined analysis in early 2025. DES combined weak gravitational lensing, galaxy clustering, and supernovae across 4 cosmic probes. DES broadly confirmed lambda CDM, but flagged one stubborn and persistent anomaly. The universe today is measurably less clumpy than the standard model predicts it should be. This is the SATE anomaly, matter clustering less intensely than every simulation predicts. 2 independent anomalies, 2 cracks in the same model. This is not coincidence. Some physicists now believe both anomalies share a single hidden cause. Dark matter may not behave the way our simulations have assumed for 30 years. Warm dark matter, particles moving faster than cold dark matter, would produce exactly this smoothing. JWST is now providing the sharpest test of dark matter models ever attempted. By observing how dark matter bends light around distant clusters, JWST maps the invisible. In early 2025, astronomers identified the largest cosmic structure ever detected, the Kipu superstructure, 68 galaxy clusters spanning 1.4 billion light-years. For scale, our entire observable universe is only 93 billion light-years across. Structures this large should not exist according to standard cosmological formation models. The universe appears to have assembled its largest structures faster than physics allows. JWST has found this same problem at the highest redshifts, the earliest cosmic epochs. Galaxies that should not exist for billions more years are already fully formed. Supermassive black holes weighing billions of suns appear just hundreds of millions of years post-Big Bang. These objects had no time to grow that large. The timeline simply does not permit it. Either our models of black hole formation are wrong, or the universe is older than we think. Now add the revelation hidden behind our own galaxy for decades. In March 2026, astronomers revealed the true extent of the Vela supercluster. It had been pulling our galaxy toward it for billions of years without our knowledge. Our cosmic maps have been missing entire continents of the observable universe. Every hidden structure changes our calculation of how matter is distributed across the cosmos. And every shift in that distribution feeds directly back into the dark energy equation. JWST is now producing the highest resolution map of dark matter's gravitational skeleton. The results are confirming something unsettling. Dark matter clumps less than our models demand. The SATE anomaly is not going away. It is getting sharper with every new observation. Now comes the most dramatic development in cosmology in a generation. Cornell's Henry Tai and colleagues published a striking hypothesis in late 2024. DESI's baryon acoustic oscillation data, they argued, points to a negative cosmological constant. Not zero, not positive, negative. The universe is not being pushed apart indefinitely. A negative constant means gravity ultimately wins. The universe has a maximum size and collapses. If Tai's hypothesis holds, the universe reaches maximum size in 11 billion years. Then contraction begins, slowly at first, then accelerating over 8 to 10 billion years. The Big Crunch arrives approximately 20 billion years from today, the universe's total annihilation. That gives the universe a total lifespan of roughly 33 billion years. Henry Tai stated directly, "It is good to know the universe will have an end." Not with despair, but with the profound satisfaction of finally knowing. But other physicists urge caution. The data is suggestive, not yet conclusive. Ofer Lahav at UCL notes, the fate of the universe remains genuinely uncertain. The Euclid Space Telescope, launched in 2023, will deliver decisive dark energy measurements by 2027. The Vera Rubin Observatory in Chile begins its 10-year legacy survey of space and time in 2025. Together, these instruments will map 3 billion galaxies and resolve the Hubble tension permanently. We are living through the most consequential decade in the history of cosmology. Every dataset that arrives either deepens the crisis or begins to resolve it. Consider what is actually at stake in these measurements of cosmic expansion. The iron in your blood was forged inside a dying star 3 billion years ago. The calcium in your bones, the oxygen in your lungs, all forged in stellar furnaces. You are not separate from the universe. You are the universe examining itself. And right now, that universe is sending us signals that something fundamental has changed. The universe is not expanding into anything. Space itself is growing everywhere simultaneously. Distant galaxies recede faster than light, not violating physics, but riding expanding spacetime. Right now, 2 trillion galaxies exist beyond our cosmic horizon, forever unreachable. Gravitationally bound systems, planets, stars, galaxies, do not expand with the universe. Only the vast distances between galaxy clusters, the truly empty spaces, are growing. The ancient carbon-rich stars in relic dwarf galaxies carry the universe's earliest chemical memory. These ancient stars provide direct evidence of how the primordial universe enriched itself with elements. Princeton's Susan Staggs described CMB images as showing the first steps towards stars and galaxies. We are, in the most literal sense, made of the universe's own investigation of itself. The cracks in our model are not failures. They are the universe revealing its deeper truth. We may be the generation that watches the pillars of modern physics begin to shift. Not since Einstein replaced Newton has cosmology stood at such a profound crossroads. The Hubble tension, the SATE anomaly, evolving dark energy, these are not separate problems. They may be different symptoms of a single profound gap in our understanding of reality. The universe is 13.8 billion years old. It has never been fully understood. And right now, for the first time, we have instruments powerful enough to ask the hardest questions. The answers will arrive within this decade. Some will confirm what we suspect. Others will shatter assumptions we did not even know we were making. That is not a cause for anxiety. It is the most exciting moment in a century of cosmology. The universe is speaking to us through its anomalies. We are finally learning to listen. If this investigation moved you, subscribe and share it with someone who still wonders. What do you think is hiding in that 95%? Tell us in the comments below.